Now let's look at an example where we've got to combine horizontal and vertical motion together. Horizontal projection refers to a situation where the initial velocity is purely horizontal, where there's no vertical component. So it could be, for example, like this. We're going to kick this football off the top of a cliff at a particular velocity. Let's say the cliff is 25 meters high, and let's give it an initial velocity, horizontal velocity of 8 meters per second. We might be asked to calculate the time it takes for this football to reach the ground, and we might be asked to calculate how far away from the cliff it lands. So if you think about the trajectory it will take, some kind of curved path like that, we're going to calculate this horizontal displacement here, which I'm going to call S for displacement and H for horizontal. So that's what we're going to find in part B. Because we've got to deal with horizontal and vertical separately, I like to try to keep them separate to avoid any confusion. So I'm going to keep horizontal on one side and vertical on the other. And let's look first at what we've got in the horizontal. Well, we know our initial velocity, I'm going to give it a little h there for horizontal, is 8 meters per second. And the acceleration in the horizontal is 0. It's almost always 0, unless you're told you have to take into account a resistance of some kind or other drag force, then you can take your acceleration in the horizontal as 0. The displacement there is what we're going to have to find, and at the moment we don't have enough to solve this, so let's go back to the vertical for the moment to calculate this first part A, the time taken to reach the ground. In the vertical, we know that the vertical displacement is 25, the object's going to fall 25 meters. We know that the initial vertical speed is 0, because that initial velocity is purely horizontal. I'm just going to put a little v in there as well. Our acceleration in the vertical is, of course, 9.81 meters per second squared, and we've been asked to find a time. So if you look at those letters, the s equals ut plus half at squared equation is again the one we're going to use here. Now, as is almost always the case, one of these pieces is going to be 0 and is going to cancel out, and in this case, of course, it's the u. The u is 0, so that bit will disappear and we're left with just two terms in here. So let's put our numbers in. 25 half times 9.81 times t squared. Rearrange that to give you 25 divided by 4.905, and that will give you 5.1. But remember, that's not the answer. You must remember to take the square root at the end of it. It's easy to forget. And that will give you 2.3 seconds. That's the time taken to reach the ground. Now that time we've just calculated is the only number which applies to both the horizontal and the vertical. So that time we can put it in over here as well. And now we've got enough information to be able to calculate our displacement. So I'm going to begin with this full equation here, s equals ut plus half at squared. But you'll notice that since it's the acceleration that's 0 this time, this part disappears, and what we're left with is just the simple version, displacement equals velocity times time. So let's put in our s equals 8 times 2.3, and we end up with a displacement of 18.4 meters. The next thing we're going to look at is what's called oblique projection. Now this means when the object is launched at an angle. So let's say that in this case the angle from the horizontal is 55 degrees, and we're going to kick or launch this projectile in somewhere with an initial speed of 15 meters per second. We could be asked to find several things here. We could be asked to find the maximum height it reached. We could be asked to find the time of flight, in other words, the total time it's in the air. We could be asked to find the horizontal displacement, in other words, how far does it travel horizontally before it reaches the ground again. Now, in this case, the only real difference between this question and what we've done before is that we're going to have to first of all resolve this initial velocity into its horizontal and vertical components. So to do that, first I'm going to redraw this velocity vector a little bit bigger so that we can see what we're doing. So there we go. And we're going to put on the horizontal and vertical components. So the horizontal component there representing the horizontal speed and the vertical one there. Now, if you prefer to see right angle triangles, you could move that vertical one across to the other side and you've got your right angle triangle, but it doesn't matter, whichever way you find easiest to do this. So, looking at that right angle triangle, the horizontal component there is the adjacent side to that 55 degrees. So with the adjacent, we're going to use cosine. So our horizontal component is going to be 15, that is the full speed, the hypotenuse of the triangle, times the cosine of 55, which gives us, for the horizontal velocity, 8.6 meters per second. Similarly for the vertical component there is the opposite to that 55 degrees. So we're going to use sine 15, sine of 55, gives us 12.3 meters per second. And now we've got what we need to progress with the rest of that question. Now, as before, because we're considering horizontal and vertical, I'm going to separate those out and deal with them separately. Now, horizontal on one side and vertical on the other. Now, the first thing we've been asked to calculate is the maximum height, which we do using vertical information. So let's have a look at what we've got in the vertical. We know that our initial vertical speed is 12.3. We know that our acceleration is 9.81, and because we have an upwards velocity here and our acceleration is downwards, it's important to put in the negative here. What else do we have? We know that at the maximum height, the vertical speed is 0. And it's the displacement, of course, that we're trying to find. So what we're going to use here then, if you look at the letters we've got, the equation that best fits is this one, v squared equals u squared plus 2as. So if we put our numbers in here, that's a 0. Don't forget the negative here. Okay, when we rearrange this, of course, as always, that negative is going to disappear when we take it to the other side. So we've now got 19.62s equals 12.3 squared. So S is 12.3 squared over 19.62, which gives you 7.7 meters. That would be our maximum height. So that's the first part of our question dealt with. The next bit of the question asks us to find the time in flight. In other words, the time it takes for the object to go up to this maximum height and to fall back down to the ground again. So again, we're going to be using vertical data, and we're going to start off with more or less the same things as before. We know our initial vertical speed was 12.3. I'm putting these here again because not all of the information is the same. The acceleration, we still know, of course, is 9.81 meters per second squared. We can no longer use the maximum height because we're not talking about a maximum height this time. What we're talking about is the object coming back to the ground again. And if you remember from previously, that means that the displacement is 0. It's come back to where it was in the vertical dimension, in the vertical direction. And what we're trying to find here is the time. So looking at that equation, looking at those bits of information, the equation we want is s equals ut plus half at squared again. And as always, there's a piece that disappears for being 0, and in this case it's the displacement that's 0. So I've got our 0 equals 12.3t plus half of minus, don't forget the minus 9.81 t squared. Rearrange this, and we've got 4.905 t squared equals 12.3 t. And as before, because we have a t squared on one side and a t on the other, we can lose that t and we can lose one of those, which makes it then easier to deal with. So now we have left that t equals 12.3 over 4.905, which gives us a final answer of 2.5 seconds. Now the last part of this question was to find the horizontal distance travelled. Sometimes this is called the horizontal range. And if you remember from before, this 2.5 seconds is the piece that we can take up to the horizontal side. So let's move back to the horizontal. Let's put our time in first before we forget that was. T's 2.5 seconds. We know our initial horizontal speed is 8.6 meters per second. We know our acceleration is 0. And we're trying to find a displacement. So again, we're going to use S equals ut plus half at squared. But because the acceleration is 0, that bit disappears and we're left a course with displacement equals velocity times time. So we've got here velocity 8.6 times by the time, which we've just calculated to be 2.5, and we end up with a horizontal displacement of 21.5 meters. That was a quick look at how to use the equations of motion. Now go and try some questions yourself.